Hello, and welcome to QuantPy. In the next few presentations, we are going to solve and analyze some of the most widely encountered stochastic differential equations such as arithmetic Brownian motion, geometric Brownian motion, Einstein-Uhlenbeck, and Brownian bridge. We will give a step-by-step derivations of their solutions, and we will also cover their probability distributions, including mean, variance, and autocovariance. We will also cover the calibration of these stochastic processes using historical data. We will then show how to simulate these equations, and how to generate their probability distributions. We hope that you will have a good understanding of these processes, and the various concepts used in the analysis of stochastic processes, by the end of the fourth video. We will start with the simplest of these, the arithmetic Brownian motion, which will take the rest of this video. The SDE of the arithmetic Brownian can be written as follows. What it says is that in a small period of time, or more formally an infinitesimal period of time, the process changes by a constant amount, which depends on the length of the period, and a random component. The first term can be interpreted as trend, whilst the second term is the random fluctuations around the trend. More formally, the first term is called the drift, whilst the second term is called the diffusion term. Note that the two parameters, mu and sigma, need to satisfy certain conditions, which essentially boil down to the requirement that they do not grow too fast, or vary too much, but we will not worry about those requirements here. Solving this equation is relatively straightforward as all the variables are nicely separated, so we can just integrate. Taking out the constants, evaluating the integral, and simplifying, we get the solution. We can interpret this solution as giving the value of the processes at t, or as giving the change in its value from time 0 to t. The solution depends on Brownian motion, which is random, and hence it is not as obvious a solution as one would see in the deterministic calculus. This was to be expected, as the whole point of stochastic calculus is that it deals with random quantities. Though it is stochastic, we can still give it a meaningful characterization. For example, we can easily derive its distribution. To see that, recall that if z is normally distributed with some given mean and variance, then a linear transformation of z is also normally distributed, where the mean and variance can be easily derived. Recall that mean and sum can be interchanged, and the constant can be taken out. The variance of a constant is 0, and taking a constant out of the variance operator involves squaring it. The reason for recalling the properties of the normal distribution is that the Brownian motion, which appears in our solution, is normally distributed with mean 0, and variance t, which is the length of time. Our solution here is just a linear function of the Brownian, so we can easily see that it follows our normal distribution. We can derive its mean and variance easily. We know the bell-shaped density of the normal distribution, and its density function, so once we know the mean and variance and the fact that the distribution is normal, we know everything there is to know about the variable. That last statement is actually not true. Reason is that a stochastic process is defined over time, so it is like a collection of random variables, and you know collection introduces covariance. So we need to include the covariance. The concept of covariance here is similar to the concept of autocovariance in time series analysis, a concept that you might know by its more familiar version, autocorrelation. So let's compute the autocovariance between the value of the process at time t and another time s, where the difference between t and s can be interpreted as the equivalent of the lag in the time series analysis, where we have used the fact that the covariance of a deterministic and a stochastic process is 0. Taking the sigma out and recalling the covariance of two Brownian motion is simply the length of the overlapping time, we get the result, and we can now relax, knowing that we know what there is to know. If you feel adventurous, then please try to calculate the characteristic function of the arithmetic Brownian motion. We will now try to get some feel for this mysterious process by using it to model some real financial data. We will use FTSE 100 index daily data over 17 business days. Normally this analysis would be carried out on multiple years of data. But we have chosen this short period so that it fits on the screen. You can look up this data series on Yahoo Finance to visualize its random behavior over time. For Arithmetic Brownian, we model the change in the value of the process, so let's generate the difference series. It is simply today value minus the previous day value. Repeating the calculations for all days, we get the series that is now going to be the main item of interests. Recall that the mean and variance of a variable can be calculated using the following formulae. Applying these formulae to our series, we get the mean and variance of the series. The standard deviation is then just the square root of the variance. Now, as per the Arithmetic Brownian assumptions, each of the daily return is normally distributed with this mean and variance. The question now is, what is the distribution of the yearly changes, as most often we are interested in the annual returns. If we assume that there are 252 trading days in a year, that is roughly 365 minus 104 weekend days, and about 9-10 public holidays, and if we also assume that the daily changes are independent, we can quickly determine the distribution of the annual changes as the sum of 252 normal variables. Mean is just the sum of the means, each of which is constant, so it is essentially 252 times the mean of the daily returns. Variance, of the sum of independent variables, again, is just the sum of their variances, so essentially, we multiply it by 252. So annualizing the mean and variance of our daily returns is easy, we just multiply them by 252. Standard deviation gets multiplied by the square root of 252. There is also another way to think about it. The arithmetic Brownian motion parameters that we had in the SDE can be interpreted as the annual drift and the annual variance. Now in continuous time, time is measured in years. That means t equal to 1 is 1 year. 1 day, which we denote by delta t, would then be 1 divided by 252, and daily mean would be annual mean divided by 252, or annual mean times delta t. So to compute annual mean, we divide the daily mean by the delta t, which is 1 over 252. Dividing by 1 over 252 is the same thing as multiplying by 252, so the answer is the same as before, but it can look different when you encounter it for the first time. Now that we have the parameters of the stochastic process, we can do many useful things with it. For example, we can simulate its paths. Let's reproduce a solution here. It gives the value of the process at time t, given the value of the process at time 0. We can generalize this to an arbitrary start time t and end time t plus delta t, meaning we are generating the value of the process after an interval of length delta t. We can then recursively generate the path of the process, substituting for the annual drift and diffusion that we estimated based on FTSE data, we get. Notice we replaced the change in Brownian by delta t times the standard normal. This is because the change in Brownian motion over delta t is normally distributed with mean 0 and variance delta t. Square root of delta t times standard normal also has a mean of 0 and variance of delta t, so the two represent the same thing. Now we can use this to simulate the daily values of the index, starting at x0, and recursively applying the above equation, with delta t equal to 1 over 252. In this case we start with 7318.5, which was the latest value of the index. We then generate a random value of the standard normal, and then plug it into this equation to get the simulated value 1 day ahead. We keep recursively generating the values of the process 1 day at a time here, until we reach our desired maturity, which we choose to be 50 days in this case. Here are a few sample paths. Notice the fluctuations come from the fact that each different day has a different simulated value of the normal distribution. That is one way of simulating the process. Recall that the value of the process at any time is normally distributed with mean and variance, depending on the length of time. So we can also generate the probability distribution of the process at any time using the normal distribution density. we do it for the terminal date of our simulation, which is 50 days. In the past simulation, had we used a large number of simulations, such as 100,000 or 1 million, then the distribution of the terminal values would have been close to the distribution we plotted here, using the density function. Let's plot the distribution of the process over time. Notice the probability distribution is a function of both t and x, but to highlight the key points, instead of creating the whole 3D surface, we will just plot its density at discrete points in time, 3 months, 6 months, 9 months, and 1 year. Here are the distributions. As you can see, the distribution drift to the right as the horizon increases. This is because the drift is positive, so we would expect the process to drift upwards over time. The second thing to notice is that the distribution flattens as the horizon increases. The values are more concentrated, around the trended mean at 3 months, but spreads as we increase t. This is because the variance increases with time, and you may recall that the higher the variance, the flatter the distribution becomes. Before moving on to the geometric Brownian motion, let's analyze the parameter estimation approach a bit more closely. We said that the drift and variance can be estimated as the empirical mean and variance of the difference series. This approach does sound a bit simplistic, but in reality, these formulae can be established using OLS, which is the acronym for the ordinary least square, and maximum likelihood approaches. We will quickly show how this can be done. The reason we want to cover these approaches is because the parameters estimation of more complicated stochastic processes requires the use of statistical and econometric techniques. So it helps to understand how these approaches work in the simplest of the cases. We will start with the linear regression. Let's say we have been given n data pairs, y and x, and we have been asked to fit a linear regression. In the linear regression, one writes y as a linear function of x, where a is the intercept and b is the slope. The epsilon is added to account for the fact that this estimate will be subject to some error. However, the errors are supposed to follow a normal distribution and are supposed to be identically and independently distributed. Recall that the ordinary least square method tries to find the parameters a and b by minimizing the sum of the residual squares r, s, which stands for the residual sum of squares. In the present case, which is the arithmetic Brownian motion, the slope is 0. We therefore set b equal to 0, and our regression simplifies. Now, if the error is normally distributed, the y will also be normally distributed, as a linear transformation of a normal is also normal. Now the linear regression estimate can be derived by minimizing the residual sum of squares with respect to a. In other words, we are aiming to find value of a that minimizes the error between the actual and our regression values, where error is defined as the RSS. So we just take its derivative with respect to a and set it equal to 0. Calculating the derivative and simplifying, we get a formula for a, which is just the sample mean formula we used. For the variance, recall that the variance of the error in the least square approach is the sum of the squared of the errors divided by the number of observations minus the number of parameters. In the present case, we have n observations and one parameter a, so the denominator is n-1, which is essentially the sample variance formula we used. So in summary, our simplistic approach to the parameter estimation can be shown to be the same as the more sophisticated OLS approach. We now move to the maximum likelihood approach. Recall that the maximum likelihood tries to find the parameters of the distribution, so that the probability of the observed values is maximized. Let's denote the series by y. As before, we saw that the arithmetic Brownian motion dynamics implies that the process follows our normal distribution, so the density of each y can be written as follows. Also recall that if a and b are independent, then their joint probability is just the product of their individual probabilities. In the present case, the joint probability of observing the y's becomes, substituting the density and taking log of both sides, we get the likelihood function. We just need to maximize it now, meaning we just differentiate it with respect to the parameters mu and sigma that we want to estimate. differentiating with respect to mu. Simplifying and rearranging, we get our formula for the mean. Now differentiating with respect to sigma. Simplifying and rearranging, we get the variance formula. Notice we have n in the denominator instead of n-1. This is because the maximum likelihood estimate of the variance is known to be biased, and to make it unbiased, we multiply it by n over n-1, so we get our sample variance formula. We hope you enjoyed the presentation, and we will see you in the next video, where we cover the same concepts for the geometric Brownian motion, which is the most popular SDE in mathematical finance.